In this video, I want to talk more about functions and their graphs. So we know that an increasing function rises from left to right. So if we have our normal graph, we know that it rises from left to right by increasing, right? And it decreases when it falls from left to right. And a constant function is horizontal from left to right. So this is our graph, right? And then right here. This has a slope of 0, which later on you'll learn more about when you get into quadratics. And you might be, well, what about vertical linear functions, right? So if we have a graph and we have a vertical, right? We know that this is not a function because from the vertical line test, we know that this does not pass the vertical line test because it is just a vertical line. And therefore, it does not have a unique output for a input. Whenever you're analyzing functions, there's a couple rules to whenever you're analyzing functions, there's a couple rules to keep in mind. So one rule is that whenever describing the domain and range, you always want to use the x intervals, right? So you don't want to use points or your y values. You just want to keep it to where you're just saying an x interval. For example, like an interval would be like negative infinity to infinity, right? And then you always use open intervals. Never use brackets unless it's included. So you don't use these brackets, right? We want to stay away from using these. And the other rule is that always look at the graph from left to right. So how you read a book, right? You read it from left to right. So if you see it like this, you read it from left to right, right? From left to right. When we're looking at these, you can think of a relative or local min or maximum as the point at which a function changes from increasing to decreasing or from decreasing to increasing. For example, if we have a function here, right? Let's say we have a quadratic, right? Right here. This would be this point right here, right there, the very top point. Oops, let me draw a little bit better. Right there, that very top point on top of the quadratic, that would be our maximum, right? And we change from an increasing slope, right? Increasing to a decreasing slope. And then we can also play this vice versa. So if we have now we have a minimum right here. And now we go from decreasing to increasing slope. And that's what our relative maximum and relative minimum allow us to do. And it applies to the same case if you have multiple curves, for example, like this. Or let me give you an example. If you get it, once you start getting into calculus and start graphing sine and cosine, you'll get used to a graph that looks like this. Right. And we can see that these have maximums, minimums, and maximum minimums. And we can see that it increases from the slope, decreases, increases. Infinitely, it switches. Another thing I want to touch up on about functions is piecewise functions. So, piecewise function is a function that is defined in pieces, with each piece defined for a particular portion of the domain. So, for example, let me create a piecewise function real quick. So we have f of x is equal to x squared plus 1, and then x is less than 2. And then another portion of our piecewise function is 2x minus 3, and x is equal to or greater than negative 2. So we can see that this will be an included value, right? This right here will be an included value because it has an equal to sign. Well, this one does not have an equal to sign, so therefore it will not include -2. And if we were to graph this, right, we could just plug in some random points, right? Um, let's plug in -2 because this is what we're given right here, right? -2. So see where we start off. So we see for their first value, right? So we plug in -2 for here. For x, we get -2 squared plus 1. 2 squared, or -2 times -2 is just 4, plus 1, which is just equal to 5. So then we can go to -2 and then 5. 1, 2, 3, 4, 5. Right here's our point. Right about there. Oops, this is, yeah. Actually, let me draw that a bit better. Right there. That is our point. Right about there. But the thing is, because it is not equal to, we understand that this will be an open circle. So this will be an open circle because it is not included, right? And then let's see, if we plug in -2 for the bottom equation, let's see, 2, -2 minus 3. We know 2 times -4, -2 is just going to be -4. And when -4 minus 3, we just get -7. So then let's go 1, 2, 3, 4, 5, 6, 7. Right. And this one, because it is included, it has that equal to. We know that it will be included. So therefore we can draw that. And two things we notice is that this right here, the first top equation, has a squared. Therefore, we understand that it will be a quadratic. So if we were to just graph this first top one alone, we know that it would look something like this, right? But because x has to be less than -2, it it shows, or it implies, that only these values that are less than -2 are possible, while everything else here is not possible. Right. So we don't graph that because it's not possible. While here in the bottom equation, we see that any of our values, including -2 and greater than, are included. And we know that this is written in the format of mx plus b, which this should look familiar because it is the same format as y equals mx plus b, which when you see this, you should automatically think of a linear function. So therefore, because we understand that it is a linear function, we know that this will have a slope of 2 and just keep increasing infinitely. And there we go. That's how you graph piecewise functions when you think of it that way. And the domain, although it does not include, for the first equation, although it does kind of look like it does not include -2 in the domain, this second equation at the bottom makes up for it because it does include it. So therefore, our domain will be infinite, will be all possible values. So from -infinity to infinity is our domain. In our range, we can see that when we look at this x value, or when we're talking about range, you want to look at the y values. So on your y-axis, what are the possible y values? We can see that the lowest value we have here is -7, right? Right here at the bottom is -7. And because it is a closed circle, we include a bracket, -7. And we can see that both of these equations, when they're graphed, just keep going up. They keep increasing. So therefore, it's from -7 to all positive y values. And because infinite infinity is just a concept, it's not a number, we'll never reach it. One is symmetry. So when talking about functions, certain functions have symmetry. Even if it's even though some symmetry makes a function not a function. For example, if we look at a circle, right, has symmetry all over. No matter the way like if I was to flip this diagonally, or if I was to fold it vertically, horizontally, no matter what way, as long as it's in the you cut it through the origin, it is always symmetric, like all the way around, no matter where I fold it, right? However, we know that a circle is not a function because it has different outputs for a certain input, right? So when talking about symmetry, we have three main types of symmetry that we discuss in algebra. So we have symmetry across the x-axis, we have symmetry across the y-axis, and lastly, we have symmetry across the origin. So let's see what those look like. So when we have symmetry across the x-axis, um, let's create, for example, y squared equals x. This graph, if you were to graph this on a graphing calculator, would look something like this, right? And we know that this does not pass the vertical line test. So therefore, it is not a function. However, that still does not mean it is not symmetric across the x-axis. So if I was to fold this horizontally, these two would be equal, like they would fold on top of each other. Well, y-axis symmetry, for example, your normal quadratics, y equals x squared, would look something like this. Draw it better. Right? If I was to fold this vertically, we know that it would have symmetry. They would line up on each other. And now we have symmetry across the origin. So these are your like cube functions, your exponential and logarithmic functions, right? So y equals 3 cubed. So we have our coordinate plane. And if I was to graph this function, we know that it would look something like this. And we can see that it has similar symmetry across the origin, like from here. So when we think of origin, don't think of diagonal origin, right? Think of your, I guess, like tangent. If so, for example, the coordinate planes, or the coordinates to get to your origin, is what makes it symmetric. For example, to get from, you have to from this point, right? Let's say we have just this point. We have to go here and then down, right? Uh, it's kind of hard, but down, right? And then we were to go back here. We see that we go here, here, right here. All right, let me actually, yeah, something like that. You'll most likely encounter symmetry from the y-axis and the origins. These are the ones you should get familiar with. You'll rarely see symmetry across the x-axis because there's not a function, so you likely won't see it. Most likely encounter functions that are symmetric across the y-axis and symmetric across the origin. There's a way to tell whether a function will be symmetric across those two. So a way to tell is if the function is even or odd. One way to know is if you're given a function, right? Let's say f of x equals x squared plus 1, right? And whenever you have just a normal integer or a value without an x, always think as this is x0. And I know this may come as a surprise, but 0 is actually even. Yeah, even I was surprised when I first learned that. But because 2 and 0 are even, we know that this will be an even function. And because it is an even function, it will be symmetric across the y-axis. So understand that even functions shows that they will be symmetric across the y-axis, while odd functions will be symmetric. Will be symmetric across the origin. But a way to prove that these values are even or odd is by plugging in negative x. So if you plug in negative x into the function of f, if you get an output of the same previous function as your original function, we know that this will be an even function. This will be even, right? But if you plug in negative x to your function, and you get an output of negative f of x, this will be equal to an odd function. However, if it is not one of these two, it is neither. It is not even or odd. So, for example, let's do f of x equals x to the power 5 minus x 6x plus 2. Then we have to decide whether it's even, odd, or neither. So first off, we can look at the exponents. So we have a 5, that's odd. We have x to the power of 1, which is also odd. But look at this. We have x to the power of 0. We know that anything powered to 0 is just equal to 1. So in reality, this is just 1 and it's still its original value. So therefore, because we have an odd, and then an even, this will be neither. This will have no symmetry across the y-axis or across the origin. But let's prove it. Let's see how we actually know for certain. So if we plug in negative x into this equation, negative x to the power of 5 minus 6 times negative x plus 2. Right? So we know that this will just be similar to anything powered. So if you have negative x cubed or negative 1 cubed, or negative 1 cubed, is similar to negative 1 times negative 1, right, times negative 1. And this will make positive 1, and then you have to multiply 1 by negative 1, which will just be negative 1. So therefore, anything negative to the power of an odd exponent will just always be negative. So we'll know that this will be negative x plus 6, because negative times a negative is always positive, plus 2, okay, is equal to f of x, right? Now let's look back. Wait, let me um we can see that this is not anything similar to the original function. We see that these two signs, right? So we see this was a positive, this was negative, have completely altered. Now this is a negative and now this is a positive. So therefore this is neither.